Okay, so now that we've talked about logarithmic functions and a few other properties, let's look at examples on how we can use those properties. So the following examples, in other words, the ones we do down here, will show how these properties, and when I say these properties, I'm referring to these ones, just on the previous, at the bottom of the previous page, right? These three properties that we talked about down here, can be used to either, well, usually you'll do one of two things. You'll either expand a logarithm, or you'll combine several logarithms. So let's say it like that. We'll expand or combine logarithms. It's a simple way to state it. So the first example I'll show you, and these are, you'll notice that these are just pretty much one-liners. They're not like, here's an example of a problem that you're going to see. Okay, now here's the solution, here's what you do, and here's your final answer. A lot of my examples follow that form, but this one is just going to be a quick one. It's not going to be of that form. So we're just going to show you a few steps. So let's say I had log base 2 of the expression 3x squared. So that's an example of something that's written as a single logarithm. And you notice that the thing plugged into the log, 3x squared, that can be written as a product of two things. Right? You can write it as 3 and x squared. So really, if the reason I'm saying it like that is so that it fits under the exact form of the first property. Remember, when you had log base a of a product, you can write that as the sum of the two separate logs, the log of each of the factors. We're going to apply that here, where our two factors are 3 and x squared. So let's do that now. So this is going to be equal to log base 2 of 3 plus log base 2 of x squared. So that's an example of expanding a logarithm. You can actually go a little bit further. If the instructions ever told you to completely expand this logarithm, you actually wouldn't stop here, because you can go a little bit further with that exponent. Remember the third property on the previous page that says if you have log base a of x raised to some power y, you can pull the power y out in front of the log, and you can write it like this instead. So let's do that, where in our case the y is equal to 2. So right, because our power is 2. So let's just bring that power of 2 right down in front of the log with our last step. So I can write this as log base 2 of 3 plus 2 log base 2 of x. Right, so that's completely expanded now. You've got an expression written in terms of several simple logs, like over here, rather than just one single log that happens to have a more complicated argument. So that's an example of expanding a log. Here's an example of combining a log. You might have something like this. Let's say I had log base 3 of 4 plus 7 log base 3 of some variable b. I'm trying to write that a little bit sharp so it doesn't get confused with a 6. Minus 10 times log base 3 of a. Okay, so that's an example of an expression that has several logs. And actually, let me go, just one last thing I forgot to mention. For the first example, log base 2 of 3x squared, notice it's very important that when we expand this into these two separate logs, both of the bases match up with the base that we started with, right? If I break this log up, all the smaller logs are going to all have a base of 2 as well. So that's important. And it's going to be important too when we're going in the other direction. So here in this example, you can see we've got several logs. They all happen to have the same base, and they're all of fairly straightforward expressions. If you might see something like this and be told to combine it into a single logarithm. And if you're ever doing that, here's the way to start. Start with these multipliers, the 7 and the 10, right? You're actually applying the third property on the previous page. Down here, you're just applying it in reverse, right? If you have a multiplier out in front of a log, you could put that inside the log as an exponent, basically going from this form to this form. It's the opposite application that we did in the previous example, but you can still do it. So let's do that with the 10. Let's put the 10 as an exponent on the a, and then put the 7 as an exponent on the b. And the first log, log base 3 of 4, let's just leave that one alone for now. Okay, so your first step, we'll just leave the log base 3 of 4, and we'll have plus log base 3 of b raised to the power of 7 minus log base 3 of a raised to the power of 10. So see, we just took those two multipliers, the 7 and the 10, and we wrote them as exponents. That subtraction here is still written here. Okay, so now be careful. Do this carefully. We'll just apply one property at a time. Let's look at the first two terms. We have the sum of two logs. We have log base 3 of 4 plus log base 3 of b to the 7. And now we're going to apply the first property. We essentially have something of this form. and we're going to turn it into something of this form. Okay, so we're going to write this as log base 3 of 4 times b to the 7. And then if we still have the log base 3 of a to the power of 10 subtracted on after. So we didn't do anything to that third term. We left it alone. It's still being subtracted. But the first two terms got combined. And then now we can apply the second property of logs in reverse. Because now we have log base a of something minus log base a of something else. We can combine it into a single log of a fraction, right? Because we got log base 3 of 4b to the 7 minus log base 3 of a to the 10. Let's write it as a single log. So we can write this as log base 3 of 4b to the 7 divided by a to the power of 10. So now we've combined all of these logs into a single log. And at every single property that we used over here, so going from here to here, and then going from here to here, they both depended on the fact that the log base is matched up. If this is log base 3 and this is log base 4, we would not have been able to combine it into a single log like this. The bases have to match up. Okay, so that's just a couple of examples. A couple more, the properties I put on the previous page, those are just the three of the important properties. They're not every single property of logs. So I'm going to state a couple more here. These have a name. They're called the cancellation laws. And really, this just formulates what it means for logarithmic functions and exponential functions to be inverses of each other. Okay, so let me write them down carefully. Now the first one says the following. So again, these both apply to what's written here, right? So let's start with a positive number a not equal to positive 1, so that it's definitely suitable for a base of a logarithm. What happens if I take the number a and I raise it to the power of log base a of x? So if I cover up the a, all I have here is just a logarithmic function with base a and x plugged in. Now let's say I use that entire expression as the exponent on an a. What's going to happen? Well, remember, you can actually answer this question. If you ever forget what this gives you, you can answer it in the following way. Log base a of x, what is this notation? Remember, it asks a question. What exponent would I have to put on a to get x back as the result? Well, whatever the answer to that question is, this notation evaluates to exactly that value. And what am I doing? I'm taking a and I'm raising it to exactly that power. So remember, this is what power do I have to raise a to get x back as the answer. Whatever that evaluates to, raise a to that power. Just by and you may have to think about what those words mean on your own to unravel it. But once you do, it just by the way log is defined, you're guaranteed to get x back as the result. And that's going to be true for absolutely any positive value of x. We need to restrict ourselves to positive values of x so that this actually makes sense. Because remember, the domain of log base anything, log base a, the domain is always just all positive numbers. So you can only plug a positive number into here. So let's say for every x greater than 0, just to be careful. Okay, and the other property, the other cancellation law says the following. If I take log base a and I plug in a to the power of x, what do I get? And it turns out you get x back as well. And why is that? Because remember, just think about what the log means, right? This whole expression asks the question, what power do I have to raise a to get a to the x back as the answer? Well, if I just stick an exponent of x on a, I'm going to get a to the x. So the answer to this is x, because if I raise a to the power of x, I get a to the x. So this is going to end up being just x. And actually, since x was plugged into the exponential function first as an exponent on the a, this is actually true for every real number x. You don't even need the restriction that we put in the first cancellation law. So this is actually true for every real number x. Okay, so those are your cancellation laws, and I'm just going to wrap this section up by just showing you an example of how you can apply each one of those. So I'm going to show these steps very carefully. These examples are not too involved. Usually you'd be encountering a little bit trickier examples than this, but this is just designed to be one minimal example for each of these cancellation laws to show you how you can apply them. Okay, so we want to solve each of these equations for x. So let's start with the first one. We've got 2 to the x is equal to 10. This is essentially just a bare bones prototype of an example of when you are going to need to use a log to solve equations. Think about what's going on here. You're solving for a variable, and the variable you're solving for appears as an exponent on either the left or the right hand side of the equation. That's probably going to mean that you're going to need to use a log somewhere. So what we're going to do is just apply a log to both sides of the equation. Remember, whatever you do to one side, you have to do to the other. This is no exception. What base are you going to use? It turns out you can actually use any base you like. But what I would recommend is if you're trying to get your hands on this variable x and it's written as an exponent on some base which is a constant, probably use that base for the log that you choose. Right? So let's take log base 2 of both sides of this equation. So you can see I've written log base 2 of the left hand side, and I get log base 2 of 10. And that, I mean, if you think about the logic there, you're saying, okay, if 2 to the x and 10 are the same thing, then we better get the same thing if we plug each of them into log base 2. So that's the logic that you use to get from this step to this step. And then now you can use the cancellation law with a equal to 2, right? We have log base 2 of 2 to the x. That's like saying log base a of a to the x when a is equal to 2. But you always just get x back. So this is the left-hand side is just going to evaluate to x. And on the right-hand side, we've got log base 2 of 10. It may look like there's nothing you can do there. And if you stop here, that's totally fine. I'll be honest. There's nothing, you don't have to go any further. This does solve the equation for x, right? But we can actually take an opportunity to simplify this log a little bit. Start by asking the question, log base 2 of 10, what does that mean? What power would I have to raise 2 up to? Or what exponent would I have to place on 2 to get 10 as the answer? Actually, it's not going to be a nice answer because 2 to the power 3 is 8. And 2 to the power 4 is 16. So 3 is too small and 4 is already too big, so it's going to be something in between, and it's probably going to be some awful irrational number. So trying to calculate it directly is not going to be very productive. But what you can do is you can simplify it. So watch this. I can rewrite this as x is equal to log base 2 of 2 times 5, right? Because 10 is equal to 2 times 5, and then I can use the fact that here's a product of two things, 2 and 5. So I can write this as x is equal to log base 2 of 2 plus log base 2 of 5, right? I can certainly do that. And then I can actually apply another property on the previous page. Remember we said that if you take the base of a log and you plug that base directly into the log, you always get 1. So if the base and the argument match up, you're going to just get 1 every time. And that's what we have on this first log. Log base 2 of 2, this is equal to 1. So finally, you're going to get x is equal to 1 plus log base 2 of 5. And that's a great place to stop, right? Like I said, it is completely fine to stop here as well. It just depends on what you're planning to do with that value once you find it, right? If all you're asked to do is solve the equation like we were here, it's perfectly fine to stop here. But there's also nothing wrong with expanding it and looking for places to simplify, like the fact that this expression here was equal to 1, so we're able to expand and simplify. So take your pick, whatever form you like better is fine. But what I don't want to see you plug it into your calculator and give me a decimal approximation, because then that's no longer exact, right? So if you got to this point and your temptation was to get out your calculator and work out what log base 2 of 10 was as a decimal approximation and then just round off from what you see on your calculator, don't do that, because that's not going to be exact. This is better because it's exact. Okay, so that's part A. Part B, we've got the opposite problem. We've actually got a log appearing in one of the sides of the equation, right? If I have, what we have is log base 3 of x is equal to 4. Over here, the variable was trapped as an exponent. Over here, it's trapped inside of a log. So how do you get it out of that log? And the answer is we're going to use a cancellation property just like we did over here, except we're going to use the other cancellation property, right? So here's the idea. Figure out what log you want to get rid of. We want to get rid of log base 3. So we're going to use the exponential function with base 3 on both sides. So what that means is you're going to do this. You're going to write 3 to the power of log base 3 of x. So what did I do? I took 3 and raised it to the power of the left-hand side of the equation. And the claim is, and the logic is this: if log base 3 of x is equal to 4, then if I take log base 3 of x and I put it as an exponent on 3, that should give me the same thing as if I took the number 4 and placed it as an exponent on 3. Right? That's the logic of what you're doing. I raised 3 to the power of each side of the equation. Okay, and then what you get now, on the left-hand side, you have exactly this cancellation property, right? With a equal to 3. You've got 3 to the power of log base 3 of x, you're just going to get x. So the left-hand side just evaluates to x. and you get x is equal to 3 to the power of 4, which actually 3 to the power of 4, that's like 3 times 3 times 3 times 3. That's like 9 times 9, you get 81. Just a shortcut way of thinking about it. But that's the answer to part B. You can solve for x and you end up getting 81. So just for good habits, if you're doing examples like these where they ask you for something specific and you're doing some work to get there, it's a really good habit to put a box around your answer. If you don't have to use a different color if you don't want to. I like to do it just because it's kind of fun. But I do expect that on your lab quizzes, when you do your lab quizzes, please put boxes around your answer. If you forget from time to time, it's not the end of the world. But if your work is hard to follow and you don't put a box around your answer and it's difficult to actually identify what your final answer is, then you may run into situations where you lose some credit. So don't fall into that. The safest thing to do when you submit your lab quizzes is to put a box around your answer. Okay, so that's the end of section 1.4. In the next video for chapter 2, that's when we'll actually officially start the course. We'll start calculus and we'll start talking about tangent lines in more detail, and we'll talk about how to get our hands on tangent lines.